right, we're going to go over some problems from 1.3, which is a little bit about different ways we can transform and change graphs and equations. Again, most of it hopefully should be reviewed from pre-calc. There might be a few new notational or conceptual ideas. Hopefully you've already read the notes first. If you have not, pause and go back and read all the notes first and then come watch the video. So I'm expecting that everyone's gone through the 1.3 PowerPoint note slides. I'm just going to jump in and do some example problems. And then tomorrow, Wednesday, in class, we'll be doing some more of the problems and going over questions on 1.3. So this first set of exercises here in 29, 30, and 31, they're asking you to determine if a graph has an inverse. Let's kind of write a few notes on what an inverse is. So if you remember from the slides, an inverse function is when we switch the range and the domain. So if my original function has an input of x and the output is y, the inverse function will have the input being y and the output being x. I don't want to call this a new name like g. I want notation that lets me know this is a function related to my original function. F is the inverse. We write f and we write it with the little exponent -1. We've clearly used exponents -1 before when you're using exponents, right? A negative exponent means the reciprocal. This is the same notation, but a different meaning. So you have to kind of understand from the context. Here I'm using function notation, so this little -1 up here tells me that this is the inverse function of my original function f. It is not telling me to do anything, it is just a naming, so I know that these two functions are related, that they're inverses. So this one, the input is x, the output is y, and this one, the input would be y, and the output would be x. A function only has an inverse function if the inverse would also be a function. So a function means for every input, there's only one output. So for a function to also have an inverse, that would actually mean for every output has to match up with only one input as well. So when I switch them, the resulting new relationship is also a function. One of the ways we can tell that from a graph is the horizontal line test. So for example, here in number 29, if you graph this, and if you don't remember how, this would be a parabola, because it's a quadratic, x squared, lead coefficient is positive, so it's concave up. It's going to cross the y-axis at 2, and it's going to have this factors to be x plus 2, x plus 1. So it'll have factors of -1 and -2. So it should look something like that. You can certainly pause and take some more time to review graphing quadratics, or use your graphing calculator or other technology to look at the graph until that's all coming back to you. But here we get a parabola, and what I notice, although the parabola itself is a function, every x has only one y, every y does not go with only one x. And I tell that from the horizontal line test. Here, for example, when y is up here at 5-ish, it crosses this graph twice, which means there are two different x's that have that output of y. That's fine for this function, but if I switch the range and domain, now if y is the input, that means that 5 will have two different answers, and so that would not be a function. So this would not have an inverse. All of these ones with the exponent of 3, the cubic functions, they're going to look something like that, but being shifted around. These do pass the horizontal line test, so they will have inverses. Not all cubic functions, you need to graph those exactly. Sometimes cubic functions might look like this. Notice this one would not be invertible, have an inverse function, because it does not pass the horizontal line test. Sometimes what we will do is look at only a part of a function so that I can inverse just part of it and it will be a function. But in general, if a function's inverse will not also be a function, the answer is no, it doesn't have an inverse function. In numbers 32 and 33 and 34 and 35, it's a little bit more about interpreting and notation. I find sometimes the hardest thing with numbers like 32 and 33 is understanding that there's really no math to do here. The answer is all words. You're trying to just understand the notation. So in this case, P is the price of an item, Q is the quantity, and we're saying the quantity of items sold is a function of the price. So in my original function, the input is the price and the output is the quantity. So here, this is going to give me the quantity sold at a price of $25, right? I see in the parentheses my input is the 25. That in this case represents the price. on part B, they are now using this inverse notation. I'm not looking at the original function, but it is related. It's the inverse function. What that means is I'm still dealing with the relationship between the price and the quantity sold, but now the input is going to be the quantity sold, and the output would tell me the price that goes with that. So this 30, that's the input, is the quantity sold. When I evaluate this, and I don't have an equation to evaluate it, but this expression, F inverse of 30, is going to give me the price at 30 units sold. 30 items sold, because that's the language they used. And number 33 is a similar type of problem, as well as 34, right? Where again, notice that they have here this inverse notation, so now they're changing it. So in general, F of X is the temperature when the mercury is X inches along. So the input is the inches of mercury, the output is the temperature. Now they're saying it's the inverse, so this input would be the temperature. So we're at 75 degrees Fahrenheit, and this is going to give me an output of how many inches is the thermometer, the mercury in the thermometer. Number 35 is going a little bit more to our transformations, not an inverse transformation, but taking an actual function and moving it around. So they want to vertically stretch this graph by a factor of 2. So that means you multiply the entire output by 2. So I take the whole x squared and multiply it by 2. And then after that, I want to shift it up by 1. So then after I've stretched it, I'll add 1 to the final answer. So what that would look like would be y equals 2 times x squared. That's my stretch of 2. And then I'm going to add 1. So this would be a parabola that's a little bit skinnier, shifted up 1. And if the order is transformed, if I shift it first, I would first add 1 to shift it. Now I'm going to multiply that entire output by 2. So that would give me part B. So the order in these transformations does matter. And the effect of reversing the order of transformation is actually going to shift it if I distribute this 2, shifts the whole thing up a little bit higher by changing the order. All right. I'm looking at a few others, the same idea with the graph transformation. Let's see if we can, copy that twice. So we'll scroll down here with a fresh paper, see if I can make this a little bit bigger for us. So in this graph, they told you that this was an original parabola and that they've transformed it a little bit. So a parabola has a basic equation of y equals x squared. We'll just put a little graph here as a review. That's a parabola concave up with the vertex at the origin. So what I've done here is basically 3 things. I have reflected the graph. I've turned it upside down. I have shifted it to the left, and I have shifted it up. So I'm going to do the shifting first. Shifting to the left, remember from the notes, would be that I'm going to add that horizontal shift in the x-axis, right? So this is going to be a shift, if I write x minus h, of h units to the right. Keep in mind, the way most students remember this is opposite sign. If I want to go to the left, I would be subtracting a negative h, which ends up looking like plus h. So if I want to shift 1 unit to the left, I want to change my input from x to x plus 1. If I want to shift up and down, remember that means you take your original output, your f of x, and you just add that shift up or down. So this is for shifts horizontally, and this is for shifts vertically. So in this case, I'm going to do plus 1 minus a negative 1 inside the x in order to shift it to the left, and then I'm going to add 3 to the resulting thing. So that would look like x plus 1, and that whole thing is squared because I'm changing my input from x to x plus 1, and then I'm going to add 3 to that afterwards. That's going to shift the whole graph up. Now if I want to flip this thing upside down, I need to make it opposite. So my final answer is going to be negative x plus 1 squared. That shifts the whole thing upside, flips the whole thing upside down, and then I'm going to add 3 to shift it up. So, oops. Get my highlighter out because I've made a big mess here. So this would be the final answer of the equation for that graph. Hopefully that's something that you're pretty familiar with, having worked with quadratics since algebra, but we're sort of looking at writing this equation from a perspective of applying all these different ways of transforming graphs. And the next concept I wanted to talk about was even and odd functions. Those were also in the notes that you hopefully read, but that might be a new idea to a lot of people. So an even function means that if I put in the opposite value input, I get the same output. So if I put in -2 or 2 for my input, the answer is the same. And what that does on the graph is it gives us, I'll do something like this, right? For whatever the graph is, if you have an even function, there's symmetry with respect to, WRT is my with respect to, the y-axis. So if I fold the graph over on the y-axis, it looks the same. What an odd function is that if I put in the opposite input, so if I put in -x, my answer is the opposite as what I would have gotten if I put in x. So if I put in -2, my answer is the opposite of what I would have gotten if I put in +2. And what that does is give us symmetry with respect to the origin. So I'll write down here 0, 0 for the origin. And not every function has to be even or odd. Some functions are neither. So applying that, we'll do one last problem together. And the last problem is going to be filling in this table. Let's make this a little bit bigger as well. So the idea here is to play around with the ideas of an even function and odd function and composing two functions. So let's do applying this even and odd. So the first one we're looking at, and the way this table works is here's my x's, so I'm using those for my inputs. And the first function we're going to look at is f. So I'm going to highlight this column. So these all represent for the function f. We don't have a formula. We're just using the pattern based on that we know f has to be an even function. So what that means is that if I have put in -3 for the output, I get the same answer when I put in +3. If I put in -2 for the input, so I meant -3 for the input, -2 for the input, I get the same answer if I put in +2. So the output for -3 is 0, so the output for +3 is also 0. The output for -2 is +2, so the output for +2 is also +2. The output for -1 is +2, so the output for +1 would be +2. G of x, they're now telling me, is odd. That means for opposite input, I get opposite output. So here they're telling me it's odd. So we're filling in the answers. They're just using the same table to save time. So here's my outputs are going to be highlighted in green, but I'm still looking here at my x column for the inputs. So since it's odd, that means the opposite input gives me an opposite output. So -3 is the input, the output is 0 according to the table. So when +3 is the input, I should have an opposite output. The opposite of 0 is still 0, so that one's going to stay 0. If -2 is the input, my output's +2. So when +2 is the output, I should get the opposite. The opposite of +2 is -2. And then for 1, we're going to get the same thing. +1 is the opposite of -1. So my output should be the opposite signs. So of +2, my output here would be -2. And then for h of x, we're going on to the last concept that we're going to consider here, which is a composition of functions. So the idea with the composition of functions is really about the order. So when they're saying h of x, they're calling that a new function, is made up of composing these two functions together. Really the key here with composition is to work from the inside out. So I'm going to start, and I think we're only going to have time here to do like 1 or 2. You start with x and you plug x into f. When you get that answer, you plug that into g. So we'll do one example with the composition. I'm going to take -1. So if I wanted to do h of -1, that means g of f of -1. Because that's how they define this function for me, and I just replaced x with -1. Now I go here, and when x is -1, f of -1 is 2. So I'm going to replace this whole thing